So, here we are in the last parameter for the physicochemical characteristic of a drug. So we have pH and pKa. pH is a measure of acidity or um, alkalinity of a solution, while later on you will see pKa is the negative algorithm of the acid dissociation and constant. So both parameters influence the ionization states of a drug, and it can affect again the solubility and the absorptions of the drug into the body. So it's significant because if we understand the pH and pKa of a drug, we can design the formulations that optimize its solubility and stability. For example, knowledge of pKa will later on aids in predicting the ionization behavior of weak or bases in different physiological conditions. And later on, when you have this information, it will give us the guidance of how to administer the drug, i.e., the suitable route of administrations of your drug. In terms of these unionized and ionizations of the drugs, the proportion of the unionized form present and thus the drug's ability to cross the membrane is determined by the environmental pH and the drug's pKa. So the pKa is the pH at which concentrations of ionized and unionized forms are equal. So when the pH of the environment is lower than the pH of substance, the unionized form of weak acid predominates. So low pH will suppress the dissociation of substance, but the ionized forms of a weak base predominates. So we give you an example. In a plasma, in a blood plasma, where you have the pH of 7.4, the ratio of unionized to ionized forms for a weak acid, example, with a pKa of 4.4 is 1 to 1000, right? So it's only 1 part unionized and 1000 part is ionized. Meanwhile, in a gastric fluid of a pH, this is the environment pH of 1.4, the ratio is reverse. It is 1000 of the unionized to 1 part of the ionized. Therefore, when a weak acid drug is given orally, most of the drug in the stomach is unionized. I mean, it is not degraded, and it's favoring diffusion through the gastric mucosa. And for a weak base of a pKa of 4 and 4, the outcome is reversed. Most of the drug in the stomach is ionized and nothing can be absorbed. Right. So to summarize that or to conclude that, weak acid in plasma versus in gastric fluid, the implication is that when a weak acid is given orally, it reaches the stomach where the pH is much lower and majority of the drug becomes unionized. So these unionized forms of weak acids drug are lipid soluble and can more easily diffuse through the gastric mucosa. And because it is lipid soluble, usually the drug will be directed to be taken after you took your meal to provide the lipid condition as well. And for the second part, which is the weak base with pKa 4 and 4, the implication is that When a weak base is given orally, it reaches the stomach where the pH is much lower and the majority of the drug remains ionized. So these ionized form of weak bases are generally less lipid soluble and may have difficulty diffusing through the gastric mucosa. In a summary, number one, the pH of environment significantly influences the ionization state of acid and weak bases. For weak acid with low pH, such as in the stomach, it favors the unionized form, promoting absorption. And the last one, for weak bases, low pH in the stomach promotes ionization, which may hinder absorption. So when we understand this principle, which is crucial in pharmacology, particularly in predicting and optimizing the absorption of drugs when administered orally. It helps in designing drug formulation that consider the physiological conditions of the gastrointestinal tract to enhance the drug bioavailability. In other words, if you want it to be consumed orally, we will design it with the weak acid nature. However, if the drug has this weak basis nature, oral digestion is not suitable. Probably we have to administer through the injection. And we have the acid dissociation constant. Basically, is a quantitative measure of the strength of an acid in solutions. So in aqueous solutions, the equilibrium of acid dissociation can be written like this. So HA is the form of the acid, for example, hydrochloric acid. So we have water, and when it dissociates, it becomes the conjugate base of the acid. And H3O plus is the hydrogen ion, which combines with water molecules to make it hydronium ion. As for the acid-base conjugate pair, we will have something like this. Acid-base, this is the conjugate pair, and acid-base water, and this is the conjugate pair. So conjugate base species formed by donating a proton, and a conjugate acid species formed by receiving a proton. So it is clear that the terms acid and base, conjugate acid and conjugate base are not fixed for certain chemical species, but are intangible according to the reaction that takes place. So the chemical species, we have this HA, the nature acid, A minus, and these ions are said to be in equilibrium when their concentrations do not change with the passing time. The dissociation constant is usually written as a quotient part of the equilibrium concentrations denoted by HA, A minus, and H3O plus. In all aqueous solutions of an acid, except for the most concentrated ones, the concentration of water can be taken as constant and can be ignored. And then the equation can be simplified by these equations. The acid in its nature form and a reversible reactions to give conjugate base plus these hydrogen ions, and hence we have this constant of this equation. Right, the Henderson's and Hasselbalch equations, the dissociations of this acid form that give you these two ions, and we have the equations at this equilibrium where we can have this constant 1, and when constant is introduced, we have this Ka, and rearranging it, and hence we will have this pKa, which is the core algorithm of acid dissociation constant. pH is pKa plus the log of ions conjugate base divided by the acid form. Comparisons of pKa and Ka values. So since pKa is the negative log of Ka, look at these lines here. So we have pKa and Ka. So pKa of -2 meaning Ka value of 10 to the power of 2. And when we have the pKa of 2, we have the 10 to the power of -2. And for weak acid, pKa of 14, we will have this pKa of 10 to the power of -14. So the smaller the value of pKa, the stronger the acid is. So we will use pKa to describe the strength of acid. It is a single number without the exponential. Okay, that's it for this part. Thank you.